But I find the longer I teach, and I've been here 25 years, the more I get tired of sort of the same questions. So if you want to talk about course material, I'm keen on talking to you. If you want to know when the midterm is, then talk to your friends or look on the web page. And we'll have a forum in which people can post questions, and if you know the answer to a question on the forum, then go ahead and answer it, and it'll save some administrative questions. And we're going to have a bunch of tests which are going to be marked by the TAs, and sometimes the TAs don't do a good job, and so people are going to want things you might want things remarked. But I hate remarking, so I'll do everything in my power to have it not happen. Certainly, you want to not give me something to mark when it's wrong, so you can check with other students ahead of time. When I started teaching this, it was before PowerPoint, so that gives you a little dating of how long I've been doing this. And I made a bunch of notes, which some publisher turned into a book. So if you want to buy the book, you're more than welcome to, or find it online. Some students say that they find it helpful, but only two out of every class, I find one or two people say they've read it, because everything you need is in the slides. So I personally am not a reader, so I wouldn't read it. I would just sort of focus on the slides. All right? Everything we need is in there. And as you might see with the mic here, I've gotten in the habit of recording the lectures, so you can go back and see what's happening. I figured I might as well do both the M and the N section of 3101, if nothing else, because about twice a term, something goes wrong and it doesn't happen, and then there'll be two chances of getting the material covered. So the key things that we have here is instead of another book, I think it comes up here. Corman is a classic book from beginning of time, and everybody in computer science should own it and look at it. But when I first started teaching here, I found the students found it too hard. They just throw these algorithms at you. All the algorithms look kind of different, and they say a little quick paragraphs about why it works, and then they go to the next algorithm, right? And so that's why I started making notes. And the challenge in teaching, I find, is figuring out what the students don't understand, right? So I try to narrow it down into a little package of, so there's these steps, which in each topic, I've developed a set of steps that you need to follow in order to develop the algorithm in question. And when I started teaching, I would say everybody do it their own way. We're all free, and I found everybody would do it wrong. So now I'm much more hard-lined. In this class, you have to do it my way. That's just all there is to it, right? I'm going to give you a set of steps to follow, and the advantage of that is if we're all doing the same things for each type of algorithm, we all follow the same steps, then I just find there's a higher chance that people will get it right, right? Not to mention it'll make it easier for the markers, right? Then this is just a bunch of old examples of tests, and then we'll have an exam. So we're not going to have any assignments. These practice tests, I recommend you sort of doing on your own. I recommend you doing them before the tutorial so that we can talk about them at the tutorial. But the reason I don't have assignments is because I find everybody does them together, and then that requires this sort of you all do them together, so we make them harder. So then you have to do them all together because you don't know how to do them, so we make them harder, and then you don't know how to prepare for the exam, right? So the most, other than learning the material, our goal here is to do well in the exam. And so the advantage of having these practice tests is they're going to be exactly like the exam, right? So it'll completely show you what you need to do in order to pass the exam. And my experience is that about on the practice tests, about half the class gets a 0. And so that gives people a good wake-up call that they need to be doing something different, right? And in fact, usually the people who really bomb it are the people who are really cocky and think they know what they're doing, and they don't follow the steps. All right? So here's the web page. If you just go to my page and click on the course, this comes up. If you want to know about specifics of this section, this term, you can go here. But what we have here is these are the key topics we're going to be covering. The relevant math, I used to spend a lot of time doing it, and people would get frustrated, and I would get frustrated. So now what we do is they get blended in to the rest of the material. When we need it, we'll pop up and we'll do a little relevant math. So even though we have slides here on relevant math, we're not going to cover those. So after we do, I added a new dot here, which is these slides, and then we're going to move over to loop invariance. All right, so here are the slides. Here, for each topic, the set of steps, which is about a 2-page document on really everything you need to know for this course, right? And then, in fact, all we're going to do is we're going to learn the steps, and then we're going to go over example after example after example. I've been curious to count how many algorithms that we do. We don't go into the little nitty-gritties of each algorithm. We just see how all of these algorithms fit into this paradigm. All right? And so then what the tests, all the tests will be is the practice test, there'll be one question, which is some new algorithm that you need to come up with, pre-post condition, and you need to follow the steps and come up with a new algorithm, right? And I also, more and more, if you have a job interview, they're going to look like the Google job interviews, in which they do that. They ask you to come up with a new algorithm on the fly, and I bet you both in the job interview and in the test, if you can't get all the details right in the time allotted, then it's not a disaster. It's can you? I think in a job interview, if you said, oh well, it seems like this is going to be an iterative algorithm. I'm going to follow these steps. What is the loop invariant going to be? They will be suitably impressed that you're going in the right direction. So that's kind of what I think all this is preparation for. And so here, practice, old practice tests, followed by solutions. And then, as I said, we've been recording it. So here's the recording it for a number of terms. I'm going to be adding them down here for the 2 sections. Everybody good? Welcome. Right, so this is kind of what I said already. Right, I'm going to give you these steps, and you need to learn them and follow them and understand them, and it's the only way you're going to pass the course. Right, and what we're going to do is go over examples of them, and we have practice tests to do them, And you know, if we were doing some sort of Shakespeare course, the expectation is that you would read the book ahead of time. Heaven forbid we have to read a Shakespeare book. But you know, so if you can think ahead of time about maybe going over these practice tests or going over the slides ahead of time, it'll help us sort of move along. What do people find about this course? My sense is that people are pretty nervous about this course. You know, how many people are a little nervous about learning this course? Yeah, exactly, right? So, but as I said, it does. I've gotten lots more and more. I get letters from people saying how taking this course really changed things for them and opened up career possibilities. And in fact, this year I've gotten about 3 letters from people who are in San Francisco, and they watch my videos and they tell me how it helped them get a job making more money than, you know, we would dream of making, right? So it's fun to get these letters back saying that they're finding it useful. Here's just some of the letters. I don't, you know, from people. I haven't put up the recent ones that have said that they haven't even taken the course from me. Right, and a lot of you are going to do badly, right? I'll tell you, the most depressing thing, other than having yet another girlfriend break up with me, that I do is mark your exams, right? That you guys, you just do so badly, right? It breaks my heart. You know, I take it personally. I think, I taught you this. How can you do so badly? So let's try not to do that badly for my sake, right? Think about my heart, right? I have to mark these things. And so just, yeah, talk to me about, if you're not understanding something, you know, talk up in class. We got a little group here. We can do fine, right? And this is just saying, I used to be a nice guy, but now I try to get more assertive because it sets up clear expectations of what we need here. And this course is going to be, it's not a coding course. You might notice we're not writing a single piece of code. It's thinking about algorithms abstractly. And let me tell you what I mean by that is if you're standing in a subway, a crowded subway with your buddy, and you needed to talk about an algorithm, would you give them code? Would you say the first line of code is I equals 0? No, you know, you wouldn't, right? You have to have a higher level of talking about this algorithm and talking about it in a way that you can think about it. Your subconscious it can bubble down to your subconscious, and your subconscious can think about it, and in such a way that you know that it works, right? We're going to see in later slides this whole idea of formal proofs of correctness, which people want to add on to what they're doing after the fact to make the professor happy or something. But here we're talking about how to think about it ahead of time so that you know that your algorithms work. And as I said, people who are kind of cocky and think they know how to code aren't going to listen to me, and they're going to do badly. All right? One thing I find when I talk to students, I say, well, what else are you taking? You know, they're taking some coding course. How hard do you work on it? You know, people put days and days into coding their big projects, right? And then I say, well, how much time do you put in this course? And they say, well, we kind of look over your notes the night before the test, right? So to me, that's not fair. You know, I deserve as much time as these other courses. So, study the material as you go and think about why we're doing what we're doing. right? And the best way by far of learning the material is not to get a friend who's an A-plus student. That's not the way to do it. The way to do it is to find somebody in the class who's failing, and you teach them the course. That's really, here's a guy. He's one of the most helpful people. He was taking my, we were doing 2011 last term, and he's very helpful. So we were just talking about how it's useful to have friends to talk to, and he's a good one. But I think he's in the wrong camp, right? Remember I told you it's not good to talk to the really good students. It's good to talk to the failing students. So don't talk to him. All right, so this is just saying, hey, let's talk about the material and teach it to each other. People get intimidated by professors, but I'm just the guy who's been here longer than you. Office hours. I'm officially supposed to do an hour of office hours. I find that the usual way is people come to my office by themselves and I talk to them. And unless you have, if you have something sort of more emotional to talk to, I would love to talk to you. But if we're talking mathematics, I find that everybody listening is good, right? Because one way to do well is to listen to what other people's questions are, right? So I've always done it kind of after the class or before the class. We've just hung out here. I said already, let's brainstorm how we're going to do that because this class seems to be full beforehand, and after class, I'm teaching 2001. So let's think about how we're going to do that. I said this already. It's hard for me to determine how hard you're going to find it, right? Said that already. This is about not coming to class, right? I do sort of look at a correlation between the people who I recognize and how well they do in the class. And there are one or two people who I don't recognize who do well, right? So I'm not saying it's impossible, right? But for the majority, the people who don't come are the people who don't do well, right? So I personally hate taking notes, so everything is going to be here. All the slides are here. You don't have to take notes. And, if your mom's sick, your cat's sick, stay home and look after them, right? You can catch up with the slide, with the videos are there. But don't do it every class, As I said, you're paying $200 an hour to be here. Come. Oops. Trip over the chairs. I was in Africa giving a talk once, and my partner had just given a talk on how it's good to be dramatic in your lecture. So I'm giving this lecture, and what do? I walk backwards and I fall off the stage. It was very dramatic, very dramatic. Everybody was pleased, laughed once they knew I wasn't dead, right? All right, read the stuff ahead of time, prepare to have good discussions, come to class. As I say, the good students can stay home, but it's the cocky students who think that they don't need to come to class that I worry about, and the lazy ones who use it as an excuse not to come. And so the tests are good because they keep us on the ball. Interact with me. All right, so today I'm a little tired, so I'm talking a little slower. But usually I just talk very fast. So your job is to slow me down so I don't talk too fast. And sometimes, I'm getting a little better at knowing what you don't know. But still, if you don't know something or your friend doesn't know something, let us all know. So in terms of questions during class, I I work hard to set up the slides so that everything builds and flows together. And if you don't understand what's on the current slide or what we've just been talking about, then definitely wave your hand around and let's make sure that you're on page, right? Because if you're not understanding this slide, you won't understand the next one or the next one, and you'll get lost, right? And sometimes people don't know what questions to ask. This isn't really a question, it's more of a statement, but I really like the one, hey, Jeff, I just don't understand a single word you're saying. Right? That's a good question. I mean, it's a statement, right? And then we can do some sort of binary search and figure out what's missing, right? But here, the negative side is if you want to talk about something we're not talking about now, that's sort of off this slide, then wait until there's a pause so that we're not breaking the flow of the lecture. So we don't get off topic. Shouting out answers. Actually, just the other day I was having a chat with friends about do people put up their hand in the classroom or not. Everybody else said in classrooms people put up hands. I find my students don't. I don't know if that's a function of me or a function of them. But the one thing I find is, one of the ways I fail at being a good teacher, I don't ask enough questions. I don't get you to interact enough. But when I do muster up a question, don't shout out the answer right away. Let everybody think about it and give a chance to the people who are struggling to learn. This is an interesting psych slide. You might have seen it before. For the first decade, there was always one student I hated. And it wasn't just me. I would survey the other class. Everybody hated them, right? And it was this sense of they were trying to compete with me and show how great they were, right? So the moral here is I'm not here to fight with you. We're all on the same team to learn the material. And the interesting thing is, about a decade ago, I made this slide, and since then, I've loved everybody. So I don't know whether it's my attitude has changed or their attitude has changed, but it's interesting. All right, so what else are we doing? Oh, here. There was one section. We're going to see how it works this term, because I have two sections of the same course. This happened a decade ago. I had two sections of the same course, and one did way better than the other. And when I asked people around what made the difference, it was because this student asked great questions. So when you ask great questions, it helps the entire class. Submit a photo. So one of the things, one of the administrative questions that I hate people asking me is, how do you submit a photo? It's documented on the page, and you can talk to your other friends, and it's really not very hard. All right? The hardest part, and I know people struggle with this, is you have to know what your last name is. I have it's complicated sometimes, with some cultures have their names all switched around, and which one is your last, I think I get confused by. But anyway, there's a column on my spreadsheet which is your last name, and I'm going to sort it, and I would love it if the pictures were sorted in the same way, right? And so you change the name of the file to be last name, first name. It's a file, and you submit it. Oh, the Z, that's a typo, because there are two sections, and so I commandeered the 3101 with no letter here to get, and then photos it goes into that. And then I think I have a macro now that every time I log on, it copies it from where you submitted it to a home page with all the pictures on it. So it won't, if you submit it and it doesn't show up on the web page right away, it's because I haven't run my macro yet. The forum is good. It says IM, but that was because I made the web the page before I knew I had two sections. Put your questions here, answer questions on here. make sure that you subscribe to it so that you get emails at the last minute saying, 10 minutes before the class, I'm dying or something. I haven't yet missed a class in 25 years, but, it might happen. I find this a little funny. If it says subscribe, that means you haven't subscribed yet. If it says unsubscribe, then you have, right? So it took me a minute to figure that out. But that was years ago. Maybe now people can figure that out. If you email me, if you put 3101 in there, then it helps me because sometimes when I'm in 3101 mode, I do a search for all the 3101 messages. So 2 years from now, you're going to want a letter of reference from somebody. So it's good that some professor recognizes you, right? This goes back to class participation. If you write me for a letter of reference, I'm going to say, hey, send me a photo because I don't know who you are. And if I don't recognize you, then all I can say is, yes, they got a C in my course, which is a pretty lame letter of reference, right? So that's all I got to say there. Doctor's notes. It irks me that you have to pay $30 for a doctor's note, and then all the doctor note says anyway is that you saw them. It doesn't say you were sick enough for an exam, missed the exam anyway. So don't bother. I don't want to see I just hate administration. I don't want to see your doctor's note. If you tell me you're sick, in fact, if you don't tell me it's nice to tell me you're sick, but if you don't tell me you're sick, the mark just goes over to the exam, right? All right, any questions about administration? All right, so hopefully we all want to be computer scientists. Hopefully we don't want to be mundane programmers. Hopefully we want to be a great thinker. I had a co-op job making hot dogs. Given the price of the ingredients today, we needed to figure out what to put in the hot dogs that day. So there's this kind of problem industry is doing all the time, right? And so if at your job you want people to tell you what you're going to code, there are fewer. I don't think there's many jobs like that anymore, right? Because especially as the systems get more complicated, and anything that's in Cormen or in this course, you're not going to have to code. It's been coded already, right? So that's, again, here I say you could just, the algorithms you learn here are not the algorithms that you're going to need in the world because your boss already knows that algorithm, right? They took the same course, right? You're going to have to come up with new algorithms, right? And that's kind of what we talked about the Google interview, is they want to know, can you come up with new algorithms, right? So what we're going to do in a course, we're going to go through so many algorithms. We can learn their code. We can trace through them. We can implement them. We can worry about all their details, right? Everybody ready for this? No, we're not doing any of that. It's not happening, right? Wrong course, all right? So instead, we're going to be at a much higher level. We're going to be surveying algorithmic techniques and abstract thinking, coming up with new algorithms, right? The goal is for you to develop new algorithms. And so all the algorithms we're doing would just be examples so that you're warmed up to how to come up with your own algorithms, right? I like to think about it, this is in my book, we want to develop ways of talking and thinking about algorithms so that, I'm going to talk about little birds and fairy godmothers, right? We have analogies. And we do it so that you can develop and think about and design algorithms and know that they work. It's not about adding proofs of correctness afterwards. It's about, as I said, it's about knowing it works when you do it, right? So here are some levels of abstraction. I could tell you a concrete algorithm. I could give you a concrete input. We could trace it out. We could say, look it gives you the right answer, right? Or we could do a little bit more. we have a concrete algorithm with an arbitrary input, which proves that for every input, it gives you the right answer, right? Or we can talk about sort of meta-algorithms. We know we can talk about iterative algorithms as a whole, or recursive algorithms as a whole, and we can try to prove that on this arbitrary algorithm and on an arbitrary input somehow gives you the right answer, right? So that's more the level we're going to be working here, right? And so as I say, on the exam, you're going to have to come up with your own algorithms. And so an important question is how formal and how detailed, do you need to be in this course, right? For me. And if you take it from other people, certainly if you take it from Andy, it really is all about those little details, right? And I'm much more of a hand-wavy person. And some people prefer that, right? And some people prefer the details, right? So you can think about which way you want to go. And so the way I think about it is what are we currently learning, right? We're currently learning these steps, so you need to follow them anally, right? You have to do those perfectly, very formally. But then within that, well, now how do you do it? Well, a picture and a little waving your hands around would do just fine, right? Does that make sense? I hate marking, for example, and sometimes if the person draws me the perfect picture, I won't even read what they write, right? Just say, okay, they got it, and let's move on, right? So again, right, are you going to get on this test during this hour and a half a perfect algorithm where every little detail is worked out? Maybe not, right? But if you get the general steps and flow of it, then that can be good. And this is just saying we only got 4 or 5 of these meta-algorithms, right? And each of them is described by 2 pages of text. You can learn them, right? There's no excuse for not knowing these. So what do we got? We got iterative algorithms, we got recursive algorithms, we got greedy algorithms, we got recursive backtracking and dynamic programming. These are kind of in one section. What's missing here is we do a section on graph algorithms, but I don't get you to develop. It's not really a meta-algorithm. It's just some concrete algorithms that you need to know, Dijkstra, depth first search. And so that's the 3rd section, and if we don't have a 3rd test, that's the 3rd one. NP completeness is all about doing reductions. Meta math. All right, so I told you the first section, the 0 section, is the math that is good for you to know, and that we're going to blend in instead of cover. But I'm really big on, I've always been big on first order logic, and this last term and over Christmas, I got really, I can get a little obsessive about something, and I've been thinking a lot about the 1090 course and formal proofs, right? So just here to tell you a little thing. If I say for all inputs there exists an algorithm, right? Or I say there exists an algorithm for all inputs, right? It's important that you know the difference between those, right? This one is good. This one should just make you cringe inside, right? It's not good that for every input you can't have a different algorithm, right? You need one algorithm that works for every input. So that's where first order logic really comes in. I find that for most sort of math problems in the world, if you can sort of write them down as a clear first order logic statement, then you can follow the steps to prove it, and life is good. We're going to do asymptotic growth. Well, you need to know how to add things up, recurrence relations. This is talking about formal proofs of correctness. We're going to. All right. So here's when I started university before you were born, obviously. in 1982, and they showed me this study that they were getting people to code up binary search, but experts, and 80% of them got it wrong. And then we can ask, well, why did they get it wrong? Did they lack formal proofs? And certainly there's a place, for Intel to check that their thing can multiply by formal proofs. And my advisor, when I was TAing for her, she gave this proof that binary search works that was so long and tedious. It was like, come on, this is just binary search, right? If you're never going to do that for a real problem, right? And so I'm not pushing here for formal methods. I'm thinking about more how to think about it abstractly, how to talk about it while you're standing on the subway so you can have a better sense that it works, right? I gave this exact slide, of course, yesterday because I'm doing two sections. If you're here twice, you'll hear the same jokes because I only have so many. Anyway, a student afterwards said that they heard in some class that things like binary search doesn't work because the arrays get too big and your integers can't index into it. And I said, oh, no, in the 80s, our arrays were not that big. I promise you, we had, when I was in high school, we had a kilobyte of memory, and then I was halfway through undergrad before we had a megabyte. We didn't have big arrays. But so it's much more of the things I'm talking about. In fact, what I think is kind of fun is we will cover binary search, and I'll say, oh, look, you could do this way or this way, and you can do this way or this way. Which way does it matter? And some combinations matter and some combinations don't matter. And I kind of figure if they chose each of those randomly, then the probability they would get it right is 25%. And 20% got it wrong. So tell me whether that's a coincidence. All right, so we're trying to understand these things more deeply, right? All right, so what are we doing here? Oh, so Donald Knuth, you may know him. He writes great math. And he says that there are different layers in which levels of abstraction that you can think about any topic. And if you want to be, I think I might have, changed it. He might have been more specific here, and I changed it to, a successful person. You need to be able to move freely between thinking about things at different levels of abstraction, right? You need to know that in the bottom, our computer is a bunch of AND gates and OR gates, right? But at the top, we have machine learning, and there are many layers of abstraction in between, right? Similarly, maybe what we're learning is something complex. This is sort of different, but we try to say the simple things and abstract. Well, what is this? Well, it's a woman who's not that happy. Right there, we got it, the key messages. And actually, let me warn you that one thing students complain about is that I give a lecture and I talk about this, and they might say, oh, I follow it all. But then when they kind of get home, or maybe they don't realize it when they're home, they don't realize it until the test, that they don't really get that we're talking about this, right? And so there's subtleties in there. And so you really need to be paying attention. And in fact, we're going to cover some simple algorithms that you know already. We're going to do insertion sort and selection sort. And you might say, oh, I know those already, and tune out. But remember, what I'm trying to teach now are these bigger ways of thinking about this. And these are just examples. And if I started with hard examples, then I would lose you for sure, right? So we're going to start with simple examples in order to learn how to do things, right? So don't tune out when we do simple examples. Right? This is, again, levels of abstraction, right? We can do the neurons in the brain versus love. Talk to your friend, right? How do you talk to your friend about algorithms, right? Or about romance, right? It's good to know all that. How do you think about a problem in a way that it can percolate down. Generally in my life I find if I have a math problem to solve, I study it long enough so that I really understand what the question's asking for, right? And then I go to sleep or I go swim, and somehow, by magic, the subconscious, can pop up these answers. So it's good to know how to talk to your subconscious. That your subconscious doesn't do Java code. That I know, right? Unless you're some really weird person. Maybe does your subconscious do Java code? I don't think so, right? Right? Paradigm shifts, I think, are interesting, right? You should all know Escher if you don't, right? If you look at the green, you get one set of pictures. You look at the black, you get a different set of pictures. And there are many things in which you can look at the same thing from different directions and give you different insights. It's kind of like what Knuth was saying, is not only different levels, but different directions at the same level. And so I've said this already. All right, so what are our topics? I told you about first-order logic, right? Here there's one girl that every boy loves versus the Pope's happy because every boy has some girl. Time complexity, you should know the basic log things. We're going to look at polynomials versus exponentials. We're going to, if your loop takes one time and then 2 times, 2, 3, 4, 5, 6, you need to add up the total time. You need to be able to solve recurrence relations because obviously we're doing recursion, so you need to know how long it takes. Our first topic, which we'll start probably next class, if not a little bit today, depending on how fast we're going. Oh, another thing, if you don't know, I never have a watch and it doesn't have my time, so anybody's is great. You can take on the job of giving me a 5-minute warning, and usually what happens is people rustle their papers, and I know that we're coming to an end. So anyway, what's this? In general, computation can be a scary thing, a complex thing, and you'll know that when you're writing a test, and you'll panic and you'll drown, right? So the key is not to think about the entire computation all at once, but to take small steps to understand the computation. All right? And so you've probably all seen this before, but I'm quite religious about it, and it's going to be a theme throughout all of computer science, is we have a simple loop that you have some data structure, and every iteration it changes the data structure somehow. And what do we have? We have a loop invariant, which is a statement, a picture, a yes-no picture about what does your data structure need to look like every time it's at the top of the loop, right? And that breaks the computation into steps, right? And so then we're saying, well, we know the precondition's true about the input, right? So now my job is, what do I do the minimal work to establish the loop invariant, right? And now, so I've seen on Reddit or somewhere a complaint that I say we fly in from Mars and the person didn't know what it means. So what does it mean? It means that we suddenly land here and we don't know how we got here. We don't know what happened before, right? All we know is that we're here and the loop invariant's true. And what is your job? Your job is, well, if the X condition's not true, you take some steps so that when you come around, you've made some progress, you'll have some measure of progress, and you maintain the loop invariant. The loop invariant's true when you get back up to the top, right? Everybody's following this? Right, and then, well, the loop, at some point, hopefully, the program stops, right? At some point, you're down here. And why are you down here? Well, what do you know? You know the loop invariant's true because you maintained it. You know we've exited true, condition's true because you exited. And so you do a little extra work to get your postcondition, right? So that's, when I talk about steps, I'm not talking about anything really too scary. Those are the steps, right? Those are the steps. A couple other things we can add in there, right? Do you have a measure of progress? Do you know your measure of progress? You know you're going to halt, right? We can add in a couple extra steps. But that's the key. And I find on tests, somebody's looking like they're drowning. So I say, hey, how's it going? And they say, well, I did all of these things. I followed your steps, but I'm panicking because I don't understand the algorithm. And I said, yeah, I don't understand the algorithm either, right? That's the whole point, is that the computation is going to be going through storms and winds and floods, and we won't understand it all, right? But if we can understand each step, then we're good, right? So similarly with recursion, a recursive program calls itself, which calls itself, which calls itself, which comes back, and it's very complicated, right? And if you try to understand it, you'll panic and drown, right? And if you try to explain that to me on a test, I won't read it. I'll just give you a 0, right? So instead, the steps are that you have friends. And you can give to your friend any instance to the problem that meets the precondition and that in some way, according to your measure, is smaller, right? So this is my instance that I need to solve. I give my friend a sub-instance. I don't micromanage them. What they do is none of my business. They give me an answer. Then I do it with another friend who gives me an answer. I combine their answers to get my answer, right? Everybody got that? We don't want to be tracing out this whole thing. We're going to do a bunch of graph search algorithms. You've seen them all before, especially if you took 2011 from me last term. We did them already. That's one of my sons. Network flows. Greedy algorithms are, you have a bunch of objects in the room that you need to make a decision about each one so that you get an overall good solution. Or solution is having a decision made about each one. And how do you do it is you look at each object individually by itself and you decide, you have a greedy criteria which ranks how much do you like that object. And when you run into the room this is my other son, and when you run into the room, you just be a 2-year-old and you say, which object, you don't study the objects in the room, you just run for the object that looks the best and you make a decision about it, right? You say, yes, I'm going to take it, no, I'm not, I'm going to color it red, I'm going to, whatever decision you need to make about it. And that's an irrevocable decision. And then you go to the next object. And the goal, the algorithms, why do we study these algorithms? It's because they're so easy. It's the first, when you're trying to come up with a new algorithm, it's the first algorithm you're going to think of. And sometimes it will work and sometimes it won't. And you need to appreciate why it works. And it has to do with long-term consequences, right? The greedy algorithm is going to say, hey, I don't want to study for my test that's tomorrow. I want to drink with my friends. That's the greedy algorithm. But they're long-term consequences, right? So the hard part of this section will be proving that it works, proving that if I commit to this decision now, that there still exists an optimal solution that's consistent with what the decisions I've made. Recursive backtracking is there are a number of things in your solution that you need to try. And when you try one of them, I like to think my little bird is giving me the answer to that question. And then that helps me formulate what I now know about the solution. The bird told me that this is true about the solution. And that narrows down the search space so that I can ask a friend to help me solve the problem. Right? And the friend and the bird together, I've got the solution. But I don't have a bird, so I try all the bird answers. And that's trying something, recursing, and backtracking. Right? So that's why it's called you try something and you back up and you try something else. But that's an exponential time algorithm because you're there's this big tree of trying. And so dynamic programming is a way of, instead of looking at every path, which is exponential number of paths, we look at every node, which is polynomial. We have a set of subproblems, and we index the table by these subproblems, and you fill in the table. It's no longer recursive. It becomes an iterative algorithm in filling these solutions into the table. So that's dynamic programming. Recursive reductions are, here's a problem where can I color this graph with a small number of colors so that every edge has two different colors? That boils down to scheduling. Can I schedule the courses so that certain courses don't conflict? Or, this is, given a circuit, is there an input that outputs 1, outputs true, a satisfying assignment? Right? Well, we're going to prove that if you can solve this problem, you can solve this problem. Right? No, but it's sort of dumb because you can't solve this problem and you can't solve this one. They're both, as far as we know, they take exponential time. But why do we do this? Well, your boss, you're going to go out to the world, and your boss is going to give you some weird problem like this and want you to solve it. And your boss will say, if you can't solve this problem, we'll fire you. And then you think about it, and you say, come back to your boss, and you say, well, boss, look, if I could solve this problem that you want me to solve, then I could solve CircuitSat. And if I could solve CircuitSat, I wouldn't work for you. So don't expect me to do it, right? So this, again, is a review of, right, these are all the topics I just told you we're going to cover. And the steps, I told you about the steps. Learn them,